Hello everybody, I'm back with another problem. Seems my camera slipped a little bit, so let me adjust that there. Love doing things in the middle of the video, don't we? Anyway, so the next problem we're going to be handling is Reif 4.5, right? Now the setup is basically as follows. We have two metals here. They both contain certain amounts of iron, which we know can be magnetized. So at first, whenever you just have your brick of metal, right, all of the spins of the iron atoms are just kind of all in different orientations all over the place. But when you get to temperatures near zero, you can basically induce ferromagnetism, and when that happens, all of the spins of these particles become aligned. So we're told this, that all of those particular particles become aligned. And when we do so, our solid heat capacity, CT, of our iron can be expressed with this function, being C sub 1 times a quantity of 2 times T divided by T1 minus 1, if and only if the boundaries of our temperature are within 1/2 of T1 and T1. The second part of this problem takes the ferromagnet that we have here, and we sprinkle some zinc into there, about a ratio of 30% zinc and 70% iron. And then when we do that, our function for the heat capacity, C of T, becomes C sub 2 times the quantity of T divided by T over 2, if and only if our temperature is between 0 and T of 2. And we're asked to take entropy considerations, in effect, in order to basically find what C1 is and what C2 is, and then also to ultimately find a ratio between these two terms. Now, in order to do so, we just take the second law that we already know, and then we evaluate it from there. Now, we can write our second law in integral form. Delta S is greater than or equal to some integral of dq over t, like that. We can write that that is equal to some integral from the initial temperature to the final temperature of our heat capacity CT of some generalized variable y times change in temperature over the temperature, right? So if we want to get the first case, where we have an undiluted metal, I'll designate that with just UD as a subscript here, SUD, is equal to the final temperature, initial temperature, of this function here, the C1 times 2 yada yada yada, right? So we can write that, we can take that and just plug it in. So we get C1 of 2 T over T1 minus 1 dt over T, like that. And then we just simply evaluate it. Let's actually do some cleaning up on the integrand here. We can distribute this T term across all of these. So what we get is T final, T initial. I'm just going to hang on to those right now. So we'll get we'll get 2 C1 T over T1 times 1 over T dt minus T final, T initial of just C1 times T, or C1 divided by T dt. If I'm not mistaken, I'm going to double check myself, see if I got a headache right now, so I don't know if I'm doing my math wholly properly at the moment. Okay, it seems I got my integrand set up properly. So now that we know that, we can plug in our boundary conditions here. This becomes just T sub 1, and then this becomes 1/2 T sub 1, same over here. Because this is the same integral, we've just decided to split it up into two parts, right? And then we can evaluate. So those cancel. We'll get T1 in the denominator. So we get 2C1 divided by T1 times T evaluated from T1 to 1/2 T1 minus C1 natural logarithm T1 1/2 T1. Because whenever we do this, 1 over t dt, when we have an integral form like this, is equal to the natural logarithm of the quotient of the boundaries. So we have this here, we can evaluate it there, and what we get once we do some further evaluation, and I'm doing this because I'm running out of board and I'm trying to think of how much space I really want to show. What we end up getting is C1 minus C1, oh my goodness, times the natural logarithm of 2. And we get this because we let this equal to T1 and then that cancels, right? And then for our C sub 2 term, I'm trying to think of what happens. Yeah, it should just cancel out too. Yeah. Things cancel. It looks, actually let's just do it. Let's actually show this. I've got room on the board. Why not? So we get 2C1 over T1, T1 minus 1/2 T1 for the first bit. So I'm not going to write an equal sign, I'm just going to write that there. So this becomes 2C1, oh my heavens to Betsy. Use my finger here. 2C1 over T1, 1/2 T1. That. Oh. Putting the cart before the horse. It's T1. Write the same thing again, 1/2. There we go. T1 like that. So we can see what terms cancel here. So these cancel, and this cancels here, and this cancels here. So this is like saying 2C1 minus C1, and that's just equal to C1, right? And the second integral should just evaluate the C1 natural logarithm of that cancels, so we have 1/2, so natural logarithm 2. So altogether, the change in entropy of the undiluted form, right, is equal to C1 minus C1 natural log of 2, which is just equal to C1 times the quotient, not the quotient, the difference of 1 minus the natural logarithm 2, I believe. Let me make sure I'm not going crazy. Nope, yep, that's right there. So that's what we get for our undiluted form of our heat capacity. So now with that in mind, I'm going to just do some erasing. You can pause it, it's a YouTube video. No one's stopping you. Nobody's stopping you. To handle the second integral, or the second case of C sub 2, when we have a diluted material, we just do the exact same process again. I'm going to call it S sub D for diluted. And we just plug in our boundaries. We get T2, and I believe it goes to 0. Yeah, I don't see why it wouldn't go to 0. Some crazy. C2, T over T2, 1 over T dt. That's what we get when we plug it all in, right? Because this is our dq component. Now we can cancel. That's nice. So we get, actually that's right, let's pull our constants out front first. I always do that, and I just work on pulling stuff out. So we get C over 2, no, C sub 2 over T2, from T2 to 0 of dt, which we can all see that this is just going to end up being C over T2, T2 0 is equal to C2, T2, T2, which is just equal to C2. Right? So if this is just equal to C2 in this case, what we can do is that we can get a ratio of these two things to effectively evaluate, to compare the magnitudes of the specific heats of the two cases. So what I mean by that is that we can set our diluted entropy, or our undiluted entropy. No, I'll do diluted. Entropy is equal to 7/10 of our undiluted entropy. What does that mean? Why am I writing it as a ratio like this? The reason why we write this ratio out is that there should be 30% fewer magnetic atoms in the diluted case as there are in the undiluted case, right? So at a particular temperature, T1, we designate it as such, we say that the entropy of our diluted case is only 70% that of our undiluted, because there's only 70% of the atoms here. So when we do this, we can plug in our changes in entropy for both of these cases, and then we can solve for a ratio of C2 and C1, which would look like this. So we could have C2 is equal to 7/10 times C1 minus the natural logarithm. Oh, once again, putting the cart before the horse. Primary Christmas. C1 times 1 minus the natural logarithm of 2. And then we just divide both sides. So we get C2 over C1 is equal to 7/10 times the quantity of 1 minus the natural logarithm of 2, which is a scalar. We have a unitless scalar, which is what we're looking for, because this would need to be unitless because we're dividing by the units of these two quantities anyway. And then you can throw this into a calculator, and you should get something along the lines of about, to 3 significant figures, 2.15, I believe. I think Reif's solution manual, which is open and available online, for you to look at, heck, I might even just link it in the description of these videos anyway, has it to a few other decimal places, like 2.148 something, but all in all, that's how you would handle this particular problem.